about everything about speech. But actually, what the title really means is that in the first part of the talk, I will talk about the rhythm of syllables and its acoustic correlates. And in the second part of the talk, I will talk about the neural processes underlying the combinatorial process that combine words into phrases and sentences. Okay, so when we talk about speech perception, basically we are talking about the process that maps the speech sound into linguistic units. And based on linguistic theories, there are many different levels of linguistic units in speech that can be mentally extracted in the brain. For example, there are like phones, syllables, words, and phrases and sentences. And how the brain decodes these linguistic units based on the acoustic features of speech is still largely a puzzle. And one hypothesis is that when we listen to speech, we first decode the linguistic unit of syllable based on a kind of speech cue, acoustic cue that's called the speech envelope. Basically, the speech envelope describes how the power of speech fluctuates over time, and it's a low frequency component of the power fluctuation. Critically, the syllable and the speech envelope are both considered as quasi-rhythmic units or features. And the rhythm of these two kind of quantities both match the rhythm of theta band oscillations in the brain. So it has been hypothesized that theta band oscillations in auditory cortex plays a fundamental role in encoding the speech envelope and to extract the discrete units of syllables from the speech envelope. And in the first part of my talk, I will revisit the rhythms of syllables and speech envelope. Basically, we want to characterize based on large corpora about how rhythmic the syllable and the speech envelope are. And we will also quantify whether the rhythm of syllable is really strongly coupled to the rhythm of speech envelope. And in the second part of the talk, I will talk about the neural encoding of phrases. So some of our previous work suggests that low-frequency neural oscillations may track, or low-frequency neural activity may track the phrases and the sentences in speech. However, there are also studies that try to argue that maybe the kind of phrase or sentence tracking activity that we observe may simply reflect the neural encoding of the properties of individual words. And during the second part of the talk, we will present some studies that try to untangle the neural encoding of words from the neural response to phrases and sentences. Okay, so I will start with the first part of the presentation, and the very first part of the presentation is the work of my doctoral student Yuran Zhang, and part of the work is in collaboration with Benjamin Mayun and Keith Dooling. So the first question that we ask is whether syllables are really rhythmic and whether syllables are more rhythmic than other units like phones and words. We all know that the mean syllable rate is around 4 or 5 hertz across different languages, but we also know that within any single sentence, there is a considerable amount of variability between the duration of individual syllables within the sentence. So if we can plot, for example, the statistical distribution of syllable duration in a speech corpus, and we can quantify the dispersion of this distribution. And the simplest way to quantify the dispersion of a statistical distribution is to calculate the standard deviation. So here, based on quite several big corpora in Chinese and in English, we calculated the mean duration and the standard deviation for phones, syllables, and words. And we calculated both the mean and standard deviation for the duration of a unit, and we also calculated the mean and standard deviation for the stimulus onset synchrony, which is the interval between the onsets of 2 units. So for the SOA, it may include the pauses in speech. but the duration measure does not include the pause. And as we can see here, as expected, the duration of syllable is longer than the duration of a phone, and the duration of a word is longer than the duration of a syllable. And similarly, the standard deviation of the unit duration also increases from phones to syllables and from syllables to words. But the increase in standard deviation may simply reflect that the units are actually longer instead that the units are less regular. So next, we normalize the standard deviation by the mean. In other words, we calculate the coefficient of variation for these 3 units. And here's the result for 8 corpora in Chinese and in English. As we can see, within each corpus, the coefficient of variation for syllable is indeed lower than the CV for phones and the CV for words. So within a single corpus or within a single utterance, it is true that the syllables tend to be slightly more regular than the duration of phones and words. However, if we analyze if we compare the results across corpora, we can see that if you consider, for example, the corpus shown in blue, the CV of the syllable for the blue corpus is actually much higher than the CV for phones and the CV for words, for example, the corpus shown by the black triangle. In other words, when the speaking style changes, actually the CV changes a lot, and the amount of change in CV caused by the change in speaking style is much greater than the difference between CV across different levels of linguistic illness. Okay, so these results show that to some extent, all the 3 levels of linguistic units, like phones, syllables, and words, they all have their own regularity. In general, the CV below 1 is considered a small coefficient of variance, which means that the on-site time or the duration of a unit is largely predictable. However, the syllable duration does not have a much lower CV than the CV for phones and words. Okay, so this is the first question that we addressed. And next, we address the question about how regular is the speech envelope. For the speech envelope, we can simply use the Fourier transform to convert the time domain speech envelope into the frequency domain modulation spectrum. And if the speech envelope is highly regular, we will expect that the speech modulation spectrum to have a very narrow peak. And if the speech envelope is not regular, we will expect a very broad peak in the speech envelope. So the temporal regularity in the speech envelope can be quantified by the breadth of or the bandwidth of the modulation spectrum. So in a previous study, we showed that the modulation spectrum is actually quite broad, and its shape is consistent across different languages. However, in this analysis, we for each language, the result is averaged over several large corpora. So it's certainly the average over many, many different speakers. So it is still possible that for a single speaker or for a single sentence, maybe the peak in the modulation spectrum is much narrower than the peak of the grand averaged modulation spectrum. And that is the question we addressed in the second study. And we quantified the bandwidth of a modulation spectrum by the smallest frequency range that can cover half of the area under the modulation spectrum. So for one possibility, individual speakers or individual sentences may have a quite broad modulation spectrum, and the center frequency of the modulation spectrum may not have great variance across speakers. And for this condition, the bandwidth of the modulation spectrum for individual speakers will be very similar to the bandwidth of the grand average modulation spectrum. And there will be relatively little variation in the center frequency. And for another possibility, it's possible that individual speakers may have relatively narrow bandwidth, but greater variation in the center frequency, so that in the average, the bandwidth of the average modulation spectrum in this case is much broader than the bandwidth of individual modulation spectrum. So by comparing whether the bandwidth of the average modulation spectrum is higher or similar to the bandwidth of individual spectra, we can analyze whether, individual speakers have stronger rhythmicity. And here's the result. The black star indicate the position for center frequency and bandwidth for the grand average over corpora. And shaded red area is the two-dimensional distribution for the center frequency and bandwidth for either each speaker in the left plot or for individual sentences in the right plot. As we can see, for both the speaker level analysis and for the sentence level analysis, the bandwidth of the grand average modulation spectrum is very similar to the bandwidth of the modulation spectrum for individual speakers or individual sentences. So this means that even for a single sentence, the modulation spectrum actually has a pretty broad bandwidth. In other words, within a single sentence or a single speaker, the rhythmicity in the speech envelope is not particularly strong. Okay, to summarize the part 1A, we see that for phones, syllables, and words, they all have their own temporal regularities. And within a single corpus or a single utterance, the syllables do tend to be more regular than phones and words. And for the speech envelope, although the speech envelope peaks around 5 Hertz, but the bandwidth of the modulation spectrum is quite broad, indicating that the speech envelope is far from being highly rhythmic. Okay, so the first part separately analyzed the rhythm of syllables and the rhythm of speech envelope. And in the next part, I will talk about the relationship between syllables and envelope. And the second part is also the work of my PhD student, Yuran Zhang. For some early work by, for example, Greenberg and many others, it has been shown that the mean syllable rate matches the peak frequency of the modulation spectrum. So it's usually believed that the peak frequency of the modulation spectrum represents the mean duration of speech. However, this kind of relationship is kind of rough because two signals may have the same center frequency, but still, the two signals may even be independent. For example, if there are two oscillators, both oscillate in the theta band, even if they are independent oscillators, the center frequency of the two oscillators will be the same. So having the same center frequency does not guarantee that two signals are strongly coupled. So in the following, I will try to analyze how strongly the theta rhythm in the speech envelope is coupled to the theta rhythm in the syllable sequence. So the first question we ask is really simple. It's simply that if we calculate the modulation spectrum based on a single speaker, we know that some speakers speak slowly and some speakers speak fast. We want to see whether the peak frequency of the modulation spectrum can track the mean syllable rate of a speaker. In other words, if I speak really slow, whether the modulation spectrum of my speech will have a lower peak, and if I speak really fast, whether my modulation spectrum will have a really high frequency peak. And here's the result for the timid corpus. And the x-axis is the mean syllable rate, and the y-axis is the peak modulation frequency. There is a statistically significant correlation between the two measures, but it's quite clear that the correlation is not strong at all. And next, we analyze two Chinese corpora that we know that the timid data set has spoken sentences, and for these two Chinese data sets, they also had read sentences. And surprisingly, I mean, for one data set, we replicate the result for the English timid, but for another larger scale data set, the correlation is way stronger. The correlation has an R of about 0.7. So both of the corpora had read sentences. So why does the correlation differ so much between them? And one possibility is that the corpus shown on the right has really long recordings for each speaker. Each speaker read many, many sentences. But for the data set on the right, each speaker only has a few sentences, like in the timid data set. So we hypothesize that maybe we can see the correlation between peak modulation frequency and the syllable rate only when we have enough data for each speaker. So for the larger scale data set that contain many minutes of recording for each speaker, we can only take a small portion of the data for analyses. And we observe that if you only take, for example, 4 seconds of recording, which is the duration of already a long sentence, and if you only have 4 seconds of recording, the correlation between peak modulation frequency and the syllable rate is actually quite poor. It's below 0.3. When we increase the amount of recording for each speaker, the correlation steadily grows, and it can plateau above at a value that's above 0.6 for most corpora. So in order for the peak modulation frequency to reflect the mean speech rate, which is quantified by the mean syllable rate, we have to have about more than 15 minutes of recording, which is really a lot of recordings. And we also analyze why we need so much recording in order to see the correlation. So here we take advantage of the structure of the timid data set. We know that in the timid data set, there are 2 sentences that are read by all speakers, and this is one of them. So we have thousands of speakers for the single sentence, and here each row in the figure is the modulation spectrum for a single speaker, and all the speakers are sorted by their syllable rate from low to high. And clearly we can see that for faster speakers, all the modulation spectrum actually have higher frequency peaks. However, for all the speakers, I mean, the modulation spectrum has a sort of complicated shape. It does not have a single broad peak. Instead, it has several narrow peaks. Typically, it has a peak below 2 Hz and 2 peaks around 4 Hz and another peak around 6 Hz. And when we look at another sentence, since there are 2 sentences that were read by every single speaker in timid, so we can compare the modulation spectra for the 2 sentences. We can see that the 2 sentences actually have very different modulation spectrum. So for the SA1 sentence, that's the famous, she has your duck soothing greasy wash water all year. And for SA2, that is, don't ask me to carry a naughty rag like that. So when the content of the sentence is different, the modulation spectrum also has different shapes. And for each sentence, the modulation spectrum has multiple peaks, and the position of the peaks all scale with the syllable rate. And here, actually, each red dot indicate the peak frequency for the highest peak in the modulation spectrum. And because there are multiple peaks, so the highest peak could be any of these peaks. So it could jump around peaks so that the correlation between peak frequency and the syllable rate is quite poor. So the conclusion of this analysis is that the modulation spectrum of a single sentence can actually carry a lot of phonetic information. So the shape of the modulation spectrum is quite different when the content of speech is different. Although the modulation spectrum is also influenced by the speech rate, because the frequency of all the peaks actually scales with the mean syllable rate. However, because the structure of the modulation spectrum is so complex, so that the correlation between the peak modulation frequency with the mean syllable rate is poor. Okay, so this analysis shows that this modulation spectrum is actually quite complicated at the level of a single sentence. And it has a lot of information that is beyond the information of syllables and the syllable rate. However, it can also be questioned. Maybe we look at the data in the wrong way, because the modulation spectrum has all the components in speech, whether it's related to the syllables or not. Maybe we should not look at just the holistic feature of speech envelope. Instead, maybe we should look at the phase coherence between syllables and the speech envelope and see whether the coherence occurs in the theta band. And this idea is actually very similar to the idea that is commonly adopted when analyzing the neural responses to naturalistic speech. For example, it's often assumed that the neural response tracking, for example, the speech envelope near 3 Hz or 4 Hz reflect neural encoding of syllables. And instead, the neural response tracking the 1 Hz-ish speech envelope reflect the phrasal level neural processing. And in the following, we will try to use simulation to test whether, for example, a neural response that tracks the onside or the nucleus of a syllable indeed only correlates with the speech envelope in the theta band. So the idea is very simple. So we just simulate a neural response that ideally tracks the syllable onside, and in fact, it's just a sequence that denoting the timing of the onside of each syllable. And alternatively, we also have a simulation that has a spike at the onside of the nucleus of each syllable. And we calculate the phase coherence between the syllable sequence and the speech envelope. And here is the coherence spectrum between syllables and the speech envelope. We can see that indeed there's a clear peak within the theta band, and the peak is stronger when we quantify the timing of syllables using the syllable nucleus than the syllable onside. However, it's also clear that there is another peak that's sort of centered around 0 Hz. In contradiction to the basic hypothesis that neural tracking of syllables only occurs in the theta band, because in our simulation, we only the simulated response only cares about the onside or the nucleus of a syllable. It does not care about anything else. However, it can correlate with the speech envelope at the very low frequency region below 1 Hz. And the correlation within the low frequency range is actually higher than the coherence in the theta band. And one possibility is that it reflects the prosody of speech. However, if we shuffle the position of all the, for example, all the pauses in speech, this peak is not influenced. However, if we remove all the pauses, for example, longer than 100 milliseconds, the low frequency peak indeed disappears. So it's the pauses in speech that generates the very low frequency phase coherence between syllables and speech envelope. However, such pauses are just unavoidable in natural speech. So when we analyze the neural tracking of speech, it's probably too simplistic to assume that only the theta band activity reflects the neural encoding of syllables, and the neural activity, for example, below 1 Hz could be reflect other level of linguistic processing. Okay, so the previous two studies both show that the relationship between speech envelope and the syllable rate is actually quite complex. But there's still, I mean, the possibility that maybe the relationship between should be characterized in the frequency domain instead of in the time domain instead of in the frequency domain, because we also know that the onset of syllables typically correspond to halves in speech, in the speech envelope, and the nucleus usually correspond to the peaks in the speech envelope. And in the next part, we try to analyze whether, for example, the syllable onset is really reliably encoded in the temporal shape of the speech envelope. And in this analysis, we still model the relationship between syllable onsets and the speech envelope. However, we did the model time domain. So we either model the relationship using a linear model, the TRF, or using a more nonlinear model, the long short-term memory model, which is a recurrent neural network model. And we can quantify how well we model the speech envelope by calculating the R square of the actual speech envelope and the envelope predicted based on the syllable onset. And we define the R square between the two waveforms as the predictive power of the TRF or LSTM model. And here are some examples. So on average, the predictive power by TRF and LSTM model is 0.1 or 0.2 when averaged over a corpora. And in the figure, I'm showing some example sentences for which the R square is similar to the R square of the average over the whole corpora. As we can see, although the R square is not super high, but clearly, I mean, the envelope predicted based on the syllable onset can already capture some very basic structure of the actual speech envelope. And furthermore, I mean, the model here is really simple because here we only know the timing of each syllable. We don't know the content of each syllable. We don't know whether it's a la or a t. So just based on the timing of the onset of individual syllables, we can already predict a significant portion of the variance of the speech envelope. And the portion is based on the nonlinear model is roughly a quarter of the total variance of the speech envelope. Okay, and in the next step, we further consider the phonetic content. So we model the speech envelope based on the timing of the onset of individual phones in the in speech. And for this kind of model, the R square is much higher and is around 0.55 for the TRF model and around 0.67 for the LSTM model. And for the example, we can see that actually the by eyes, I mean, the simulated envelope is quite similar to the actual envelope of speech. So basically, the results show that the timing of phone onset can explain more than half of the variance of the speech envelope. Okay, to summarize part 1B of my talk, basically all the conclusions were already said before. So first, the timing of syllable and phone onset can explain a significant portion of the variance of speech envelope, but there is no simple frequency domain mapping between linguistic units and the speech envelope. And also the modulation spectrum of speech is sensitive to both phonetic information and the speech rate, so that the relationship between peak modulation frequency and speech rate is quite complex. Okay, so now I will go to the second part of the talk, which is shorter, and it's about the neural encoding of phrases. So some of our previous studies argue that when we listen to speech, neural activity low frequency neural activity will track the mentally perceived phrases and sentences in speech. But it has also been argued that maybe this kind of phrase or sentence tracking activity may reflect, for example, the neural tracking of the semantic or syntactic property of individual words. For example, the reason is that in our experiment, we usually use sentences of a highly regular structure. And for example, a lot of sentences have the structure of an adjective followed by a noun, followed by a verb and a noun. In this kind of sentences, the sentences were repeated at a rate of 1 Hertz, but at the same time, because each sentence has a single adjective, and the adjective is always at the beginning of a sentence, so the adjective also repeats at a rate of 1 Hertz. And because each sentence has 2 nouns, and the nouns can repeat at a rate of 2 Hertz. So it has been argued that even if the brain only encodes like, for example, the part of speech information or the semantic properties of individual words, because I mean the nouns have different semantic properties than verbs, for example. And even if neural activity is only sensitive to the syntactic or semantic level features of words, maybe it will also show very low frequency fluctuation. And to test whether this explanation is plausible, we previously had this kind of had an experiment that asked the participants to learn an explicit rule and use that rule to chunk a sequence of nouns. And although I won't go into the details of the results of this study, basically there we see that when the listeners are explicitly doing the chunking task, low frequency neural activity in their brain can track the chunks that are defined by the explicit rules. And because we can teach them different rules when they are exposed to the same kind of speech stimulus, we can distinguish whether their neural activity is tracking the rule-based chunks or the property of individual words. And there we see that is actually the chunks that is driving the neural response. However, it has also been argued that, they are doing an explicit chunking task. So, but during natural sentence comprehension, we do not have this kind of explicit syntactic task. So it's still a puzzle whether, the neural tracking of sentences could reflect the neural encoding of word properties when we listen to sentences when doing a natural speech comprehension task. So to address this problem, we actually designed a new experiment that takes advantage of the regular structure of sentences and use the regular structure of the sentences to design control conditions to tease apart the neural response to words. So in this experiment, we had 2 kinds of sentences. One kind of sentences is a noun followed by a verb, like airplane took off. And another kind of sentence is a verb followed by a noun, like warm up red wine. And for each noun, it has 2 morphemes, and it could either be a single noun, a single word, or it could be a noun phrase that consists of 2 words. We do not distinguish these 2 conditions because in Chinese, the morphemes are clearly defined, but the words are not defined. And there's a lot of debate about what should be called a word and what should be called a phrase. So here we simply, do not distinguish and simply refer them as a verb or a noun, but it may actually involve some level of combinatorial processing already. And because we have this kind of noun-verb sentence or verb-noun sentence, we can take out, for example, the noun in the noun-verb sentence and put that in a list of nouns, and take the noun in the verb-noun sentence and put that after the noun in the noun-verb sentence, so that we can construct a noun list that match all the nouns in the sentence condition. And also within every 4 phonemes, the position of the nouns in the sentence condition matches the position of nouns in the word list condition. And we can do the same thing for the verbs. We can construct a sequence of verbs. And when we have the two kinds of sentence sequences and two kinds of word lists, we can simply average the neural responses to the sentences and the neural responses to the word list. And for any neural response that encodes the property of individual words, it should match in the averaged neural response. So we can subtract this word level tracking response off by simply taking the difference between the mean response to the sentence and the mean response to the word list. And in the experiment, we recorded the neural response using MEG, and the listener simply detect jumbled morphemes like airplay, wine out. So it's not, it does not construct a meaningful sentence or a meaningful word. If we, define word as the two morpheme structure. So, and here is the neural response. And also we had two conditions. In one condition, each kind of sequence is presented in a separate block, and in another condition, all kinds of sequences are just mixed, and the result do not really differ between the two conditions. So I'm only presenting the result from the mixed condition. So here I'm showing the waveform of the neural response to the noun-verb or verb-noun sentences for one representative channel, and also show the power spectrum of the neural response that's average over all the MEG channels. So in the time domain waveform, you can see, so the boundaries between sentences are marked by a vertical green line, and the duration of each sentence in the condition is 1.2 seconds. So for each sequence, we had 10 sentences. So the total duration of the stimulus is 12 seconds. So we can see that basically, even if you just look at the waveform, we can see that the main periodicity occurs at the rate of the cycle of sentences. And in the power spectrum, we can see that there's a clear peak at 1/1.2, which is the sentence rate. And we can also look at the response to the word list. And this time, in the waveform, we can clearly see that, basically the frequency of the response doubles. But still, there is a weak component that is evident in the spectrum that is still at 1/1.2 hertz. So indeed, even if there's no syntactic structure at all, there could be some level of neural activity that reflects the properties of words. And here, the 1/1.2 hertz response is stronger for the verb list, possibly because one of the verb is always a transitive verb, and the other verb is always an intransitive verb. So this kind of switching in the property may generate a 1 hertz response. But still, the 1 hertz response for the word list condition is much weaker than the sentence rate response in the sentence condition. And we can subtract the response to the word list from the response to sentences and get a sort of purified neural response to sentences. And there we can clearly see that the response oscillate or fluctuate at the rate of sentences. And in the spectrum, it's also clear that the response is strongest at 1/1.2 hertz, which is the frequency of individual sentences. Okay, to summarize this part, we observe that low frequency activity can indeed track sentences, even when the property of words are fully controlled. Okay, to summarize the whole presentation, I think one message is that we can observe temporal regularity for multiple levels of linguistic units, such as phones and syllables and words. In the future, of course, we will also try to characterize the rhythm for phrases. And the speech envelope can indeed carry information for multiple levels of linguistic units. However, this kind of relationship is complex rather than simple. There's no simple frequency domain one-to-one mapping between linguistic unit and speech envelope. And finally, because the speech envelope is too complex, it's still, I mean, a good idea to just remove phrasal level and sentential level cues in the speech envelope to isolate the neural response that's related to more abstract linguistic processing. And by removing the phrasal and sentential level linguistic cues, I mean that we can do a frequency tagging study. And here we extend the frequency tagging paradigm to fully control the neural responses to the properties of individual words. And after controlling that, we still see a neural responses that's related to the combinatorial part of the processing. Okay, thank you all for listening, and I also want to thank members of my lab. Thank you.
Thanks for this great talk. So now we can have Q&A session. So anyone wants to ask question, can raise your hand.
There's something in the chat. No?
No? Anyone?
Maya, may I?
Hi.
Hi.
Hello.
Thank you. This was wonderful. I studied
Thank you.
the temporal structure of spontaneous speech and how it interacts with the sentence structure in English and Korean and Czech. And I have like 100 questions. So like one of the things is like you compare Chinese, this is Mandarin, right?
Right.
Yeah, and English. And you had in your part 1b, you had this plot where there's a difference between the syllable onset and coda, right? Between English and Chinese. And have you ever, like, there are differences in the prosody of Mandarin and English?
Well,
how
we
much
haven't
information
really, looking. Sorry.
So how much information is in the variation in vowel duration and the actual variation in syllable duration? There are differences in how these behave across sequences, or I would suspect there to be some. Have you ever thought about something like that or analyzed that?
We haven't fully looked into this. However, my intuition is that for Chinese, the structure of a syllable is highly simple. It's just a vowel that's either preceded by a single single consonant, or followed by a consonant. And if it's followed by a consonant, it can I think it can only be a nasal. So the structure of syllable is very simple. So we don't have, for example, a very long consonant cluster at the beginning of a syllable, so that the time interval between syllable onside. By the way, so here we define the syllable nucleus simply by the onside time of the vowel. So the time difference between syllable onside and the onside of the vowel is relatively short, and so it's at most one consonant. But for English, I mean, I think the distance is more unpredictable. I mean, because there could be no consonant or quite several consonants. Well, and I think, I think the vowels are more tightly related to the peaks in the speech envelope. So, so for Chinese, I mean, the syllable onside is coupled to the onside of the nucleus. So, so it can better. And I think the nucleus better correlates with the speech envelope, so that the syllable onside better correlates with the speech envelope for Chinese than English. Just my intuition.
I just find that the difference is really interesting, and I've always wondered, you know, if these are two different dimensions, does the variation in the vowel duration and actually the frequency distribution across a sequence of syllables, then they don't contribute equally to discrimination in speech. And then it would be interesting, like if they're like differences between Chinese and English, where vowels just carry more information in Chinese than they would in English.
Yeah, I think, I mean, it would be interesting to look into this. I mean, it'd be more interesting, of course, I mean, if we can compare multiple languages, like, and because, I mean, English is a stress time language, Chinese is sort of unclear. But if we include like a more syllable timed language, I think it'd be a more interesting comparison.
Yeah.
But I mean, our difficulty is that for both Chinese and English, we know how to segment the syllable. We know how to find the boundaries between syllables. But for all other languages, we don't know how to, I mean, clearly define the boundary between syllables. We don't know how to segment the consonant cluster. So that's why we didn't. So of course, I mean, for many different languages, we now have big speech corpora, but it's just that we don't know how to define syllables for other languages, so we didn't analyze them.
Yeah, but actually the vowels do a really good job if you just track the vowel variation in the vowel duration across sequences. That's also, it's like, it's a good.
Oh yeah, for that, right, we can do that for many different languages. And I think for the vowels, I mean, that's the syllable nucleus condition in this plot. I mean, it's largely comparable, I think, for Chinese and English.
Yeah.
Although we didn't statistically compare them.
Okay, can I ask one more?
Sure.
In the last part of your talk, you were comparing word lists and sentences.
Right.
And one thing that I always wonder, like that you would have more activity in the 1 Hertz. What is it? I think it's a couple of slides further on.
This one?
That's right, yes. We had these differences between word lists and sentences. Do you think that reflects processing, or could it be like some kind of fallback mechanism once you can't find?
It could be, very good question, but clearly we cannot really distinguish the two. We don't know, I mean, whether it's the direct consequence of combinatorial processing, or whether, as you suggested, I mean, it could be some feedback. But even if its feedback is the sort of the consequence of combinatorial processing. Yeah.
Okay. Terribly interesting work. Thank you so much.
Well, thank you.
Any other question?
I have a question.
Hello.
Can I? Yeah. Hi, thank you for your presentation. It was very nice. So I have a question about let's say, the underlying mechanism behind these responses at the, let's say, at these peaks more related to combinatorial processes, no? So when you were talking about the first part about more syllable tracking and envelope tracking, you were very explicit about the theta band oscillator, right? And I wanted to ask you if you think that for these more combinatorial processes responses, do you think there is a delta band oscillator behind it? Do you think it could be more evoked responses, that because the frequency tagging paradigm uses periodic stimulation, then what do you think? I know it's a never-ending debate, oscillation versus earpiece, but what do you think about all of this?
It's a very good question. As you said, I mean, there's a lot of debate on this. Well, I use the term oscillation really loosely. In the first part, I do talk about theta oscillations, but even there, for example, even if we just play, for example, unknown speech to a listener and we can record this kind of theta band activity, even for that condition, I don't know if it's really oscillation or evoked response, because actually the two are not really clearly defined. Because I mean, even for evoked response, I mean, some people argue that maybe it's due to phase reciting of ongoing oscillations or other things. And even for oscillation, I mean, it could be just defined in many different ways. I mean, there is no single thing that's called a theta oscillation or delta oscillation. At the biophysical level, it could be generated by many different mechanisms, and just phenomenologically, for different people, I mean, oscillations are defined differently. For some people, it simply means that the oscillation is something that's always there. So it's an oscillation if the property of the response is the same before and after the stimulus. And for other people, maybe it only means that the response is still there after the stimulus is off. So there's some kind of waning. And there could be also other kinds of definitions. And I think, I mean, because the definition is not clear, so it's hard to tell, I mean, whether it's a evoked response or a oscillation. But there's another component in the question. So you asked whether, for example, the kind of phrase and sentence response could be delta oscillation. There's last year there was the very interesting perspective by Kazanida and Alexander. And for that perspective, they take delta oscillation, they define delta oscillation as the oscillation within a frequency range that's maybe between like 1 and 3 hertz. If you define, for example, delta oscillation in a very with clear borders, I mean, it's almost guaranteed that it cannot really explain the kind of neural responses, because as argued in that perspective paper, I mean, if you present, for example, long sentences, I mean, the response tracking the long sentences will certainly go below the boundary between the delta oscillation, for example, they define or other people define in their studies. In my opinion, I mean, I certainly do not expect that the delta oscillation, for example, defined in even the frequency range of the delta oscillation is defined in very different ways across different studies. So I certainly don't think that, for example, the frequency range defined in one way could indeed, I mean, provide a lower limit for the neural response that can track the sentences. In other words, I mean, for me, I mean, if your sentence is like 3 seconds long, there's no problem that neural activity can track this kind of 3 second long sentences. But of course, I mean, few people study that because we also know that there's the 1/f background spectrum in the neural recording. So if you go to the very low frequency region, you'll face a lot of strong noise. So it's hard to just clearly measure the sentence tracking response in the very low frequency region. But on the other hand, I mean, I also believe that, I mean, this kind of tracking cannot just go to infinitely low frequency, because, I mean, suppose I speak a sentence that's 2 hours long. I don't believe that there's a neural response can well track the 2-hour long sentence. First, because, I mean, it's basically, we have to chunk very long sentences into smaller chunks. And even during speech production, we cannot really just output a very long sentence. We need smaller chunks. So in my opinion, I mean, this kind of low frequency activity can track just whatever chunk that you perceive during online speech comprehension. And as long as you can perceive the kind of unit, there will be a neural response that's phase locked to the perceived chunk.
Cool. Thank you. Thank you for your very comprehensive response.
Thank you.
Okay, any other question? Anyone?
Hello.
Hello?
Yeah, I have a question. I don't know, can you hear me?
I can.
Okay. Well, a wonderful work. I'm very amazed about all the work that you have done. My question is very, very specific, very, very little. Is related to these models that you feed to predict syllable boundaries based on the syllable information and the phone onset. And it's a very specific phonetic question, actually. It's not a phone onset basically a feature of a syllable at the end of the day?
Oh, I'm not saying, I mean, the onset of phones are features of syllables. No, I mean, basically, I mean, they are features of phones.
Yeah, but I mean, I that's what I got from your presentation. But my question is not like kind of the other way around. Like, in order to get something, a feature like a phone onset, it's not like you can isolate a phone and determine it based on a single phone, the phone onset. The phone onset is determined by what is preceded, right? And that should be the previous syllable. In that sense, it's not the model that tries to predict syllable boundaries based on the phone onset. At the end, more kind of is using information at the end of a syllable, but more precise information of a syllable instead of a phone.
Sorry, could you repeat your
Sorry. I overcomplex. I made a very complex question. Sorry. Basically, that the phone model, the model that predicts the syllable boundary based on the phone onset, at the end of the day, is maybe using information that is actually belongs to a syllable. And not necessarily, basically, I'm thinking on the size of the unit that you are, that is underlying all this process. That because at the end, the phone onset is a feature that necessarily depends on the syllable, not in the individual phone or sound. So my question is, it's not at the end two models that both rely on the syllable as a unit. It's just that the phone onset model relies on more specific information, more rich information of a syllable.
Yes, I think, I mean, actually, probably a better way to just derive a syllable level representation is to, is not to, I mean, break up a syllable into phones, is instead to, for example, just separately model the response to each syllable, like da or pa. But the number of syllables, I mean, is great. I mean, we have so many different syllables in English, and even for Chinese, I mean, the number of syllables is not so small. So it's just hard to fit a model that considers for that separately models each syllable. And for the, I guess my the motivation to do this is that, for example, if you have a stop like T or something like that, a symbol like T, I mean, there's certainly a very clear, I mean, onside for the syllable. But if you have a syllable like la, probably, I mean, in connected speech, there's probably no chof at all, maybe at the boundary between syllables. So we just want to have a model that can consider, I mean, this kind of difference between syllables. But of course, I mean, breaking up the syllables into phones can introduce other information. For example, it can tell, I mean, when is the onside of a vowel or individual consonants. So that is additional information that that won't be available for a syllable level representation. But also, especially for this kind of sort of large big data approach, actually the label for the phone onside is usually not of very high quality. And we also did some automatic labeling for the phone onside, and that, of course, is not very high quality either. So I think, I mean, so basically, I'm saying that, I mean, here we are considering the onside of phones, but actually the phone onside, the timing of the phone onside may not be so precise either, because I mean, it's actually hard to label precisely the onset of each phone. So I think our main purpose is, as I said, I mean, it's just to distinguish, I mean, different kinds of syllables.
Okay. Yeah. But actually, I was wondering, how do you determine the onset of each phone? I was like, wow, that is like, it sounds very specific. So, but how did you do that? How do you establish, how you measure the onset of each phone? Because I think that there's
for some
ways,
data set like, for some data set like timid, I mean, there are hand labeled boundaries between of different phones. But as I said, I mean, it's not of great high quality.
Okay.
And for some large corpora, we just use a simple automatic algorithm to find the boundaries between different phones.
Okay, I see. Thank you.
Thank you.
Okay, I think we can take one last small question. Is there anyone? Yeah.
Can I speak?
Yes.
Okay.
Lorenzo.
Hello, Nai. Thank you for the great talk.
Thank you.
Sorry. So during your presentation, you mentioned also in the end as a take-home message that the modulation spectrum carries a lot of information that is complex, and it's maybe going also beyond the acoustic syllable rate, the information that it carries. And in this particular study that we also see on the slide, you mentioned that adding phonetic information drastically improves your predictive power of these models beyond the time information. So I was wondering if the temporal regularities of these phonetic features can account for some of the increase in power that you can see also at the rate of your combinatorial responses in the study that you see later. So in the next study that you presented, you seek out to isolate these combinatorial responses, and you do clearly show that the peak at the sentence rate is clearly the one that is most different between conditions. But here you are comparing sentences like versus word lists, and I was wondering if lower level acoustic features are also isolated away from this combinatorial class.
Okay, very good question. And maybe I should just add another slide. So as I mentioned, I mean, the last study is a frequency tagging study. So each morpheme here is independently synthesized by the computer. So there's no co-articulation or prosodic cues at all. And also, for example, the morpheme in the sentence condition is exactly the same as the morpheme in the word list condition. So they are not just separately produced by real humans. And for this kind of, so as I might have mentioned in the conclusion, so in this kind of frequency tagging paradigm, so we basically remove all the speech envelope information that's related to like words or phrases or sentences. So we did that on purpose because if we do not remove those cues, there could be, I mean, acoustic cues that's encoding, for example, the boundaries between sentences or phrases, so that even if we see a neural response tracking the sentences, we cannot really tell whether the neural response is tracking the mentally constructed structure of a sentence, or is simply tracking the acoustic cues that are available in speech. So in this kind of frequency tagging paradigm, we always remove the prosodic information, and if we apply a coherent spectrum analysis for the materials in this kind of stimulus, there is actually only a sharp peak at the syllable rate, and not at any other frequencies. So In other words, I mean, only the neural response at the syllable rate or the morpheme rate is potentially confounded by the neural encoding of the speech envelope, and all other neural responses cannot really be explained by the speech envelope.
Yeah, thank you for your answer. If I can quickly follow up, I was thinking also about this the possibility of having rhythmic phones in this stream. Like I think I understand that when you take off pauses, for example, you do see on the syllable rate, and that's clearly an acoustic cue, but another type of elements that could be also rhythmic in your stream could be maybe characteristic of phonetic features that can give some contribution to the acoustic envelope. So.
Sorry, I didn't hear the first part of the question clearly.
I was thinking about, in a word, phonetic regularities of individual phones. Yeah, if they could be also occurring at that rate, because I do see that you had the same words, but in the noun conditions, like there could be phones that are repeated at the same position across the phrase, the noun phrase. And that's
okay. So do you mean that, for example, we should do a analysis of how for example, the phone sequences or the morpheme sequences correlate with the speech envelope?
Yeah.
Okay. Yeah, I think that's a good suggestion. We can certainly do that.
Yeah, so I think it's time. So let's thank Dr. Nadine's great talk, and thank you, everyone.
Thank you.
Thank you.
Okay, bye-bye.
Bye.